me?
Yes.
But seems that
Position.
hear us.
Yeah.
Hi, Zuxin, can you hear us now?
Yeah.
Great. Okay. So thank you so much for your patience and welcome to attend our Safe RL online seminar today. And today we are very happy to have Zuxin to give us a talk. And Zuxin is a fourth-year PhD at CMU. And he also spent summers on DJI, Neural, and Amazon previously. His research interest lies in the reinforcement learning, imitation learning, and particularly their robotic applications. And he is now interested how to safely, robustly, and efficiently apply the reinforcement learning to real-world safety critical applications. And today, he will share his recent work on how to achieve the robust, efficient, and safe reinforcement learning. So without further ado, let's welcome Zuxin.
Yeah, thanks for the introduction. So it's my great honor to present here. I'll share two of my recent works. So I will mainly cover two topics today. One is about the robustness of safe RL, and another is about how to learn a safe policy from offline data sets. So let's first focus on the first robustness part. This paper has been published on iClear this year and is collaborated by Google and UIUC. So, first, why study the safe RL? We know that the safe RL has achieved great success in computer vision games, but we haven't seen much applications to real-world applications, and a lot of potential issues prohibit us to deploy them to the real world. And the safety is one of the major.
Hi, Zuxin.
Yeah.
We cannot see your screen.
Oh, sorry. Let me check.
Oh, yeah, we can see your screen now. Yeah.
Oh, so when I click when I want to share the full screen.
Zuxin just told me that his computer is down, and he will be back in a minute. Sorry again. Yeah, and thank you for your patience.
Oh, I'm so sorry about the delay. So I will not share full screen this time. Yeah. Okay.
Yeah, we
Can
can
you see my
see.
screen now?
Yeah, yes.
Can you see my screen now?
Yes, yes.
Okay. Cool. So yeah, I will first talk about this ICLEAR work about the robustness of safe RL on the observational perturbations. We can skip like this kind of motivation because I think most of you are familiar with safe RL. We can let's directly jump to the definition part. So we consider the safe RL problem under the CMDP framework. We compared to the classical MDP, we introduce additional cost function to characterize the cost for violation of constraints. And we will also have the reward value function and the cost value function respectively. And our goal for safe RL is to maximize our reward while satisfying the certain constraints. And there are actually multiple definitions for safe RL. For example, the safe deployment by the expectation constraints, which means that we want to maximize the reward value function and also want the cost value function to be smaller than certain threshold. Some other definitions is like safe deployment with per state constraint satisfaction, which means for each state we want the policy we want our state action to satisfy certain constraints. And there are some also other definitions like safe exploration, etc. But in this talk, we will mainly focus on the first definition, like safe deployment via an expectation form. Okay, so then let's briefly talk about some popular algorithm to solve the safe deployment problem. We call this safe RL objective. We want to solve this constraint optimization. So the simplest way and the most widely used way is to convert it to a Lagrangian formulation by this formula. So we add additional Lagrangian multiplier lambda to penalize the cost of violating constraints. And if we iteratively solving the policy and the Lagrangian multiplier iteratively, we can obtain a good policy, a safe policy. For the Lagrangian-based safe RL methods, we have two steps. The first is to fix the Lagrangian multiplier to optimize the policy pi. This step can be done by any policy-based RL methods. And for the second phase, we fix the policy pi and to optimize the Lagrangian multiplier lambda. And in this stage, we could do one-step gradient descent or use some control-based methods such as the PID method mentioned in this ICML work. So then let's see some performance of the one method of the Lagrangian-based method by combining it to the PPO algorithm. So left figure shows the cost values and also the Lagrangian multiplier values. We can see it will converge to some target threshold we predefined. And the right one shows a video demo for the learner policy. So this is called the car circle task. The robot needs to move in a circle, but within a safe region, within the two yellow boundaries. The robot may gain more rewards if it's more close to the blue circle, but if it go cross beyond the two yellow walls, you will receive a cost for constraint violation. As you can see, the PPO Lagrangian actually can learn a very good policy. He can the agent basically can stay very close to the safety boundary to maximize this reward while stay safe. So before introduce the robustness problem, let's first rethinking about some definitions or properties in safe RL. I want to mention that those definitions are widely used, naturally exist in the safe IO setting, but it's seldomly being formally discussed. So we will, but they will be used in our work. So I will introduce them. So first is the feasibility definition. The feasibility basically means we want the all the policies that satisfy the constraints. We regard them as feasible. So we can see this figure. So this figure represents represents the policy space, represents the policy on the value function space. So the x-axis is the reward value function, and the y-axis is the cost value function. The kappa is our some predefined constraint threshold, and each point on this so each point within this contour represents the policies with corresponding values. For example, the point here means it has represents the policies with corresponding reward return and cost return. So in other words, all the policies below this constraint threshold and within this contour can be considered as feasible policies. So with this definition, we can easily define what is the optimal policy in safe IO setting. So the optimal policy basically means we want to achieve the maximum reward while also satisfy the constraints. And we also introduce another definition called temptation. So for the temptation policy, it means it denotes the policies that has higher reward return than our optimal policy. So why we call it tempting? Because we have like this lemma 1, all the tempting policies are actually unsafe. So which basically means if you want to achieve more reward than the optimal policy, you must sacrifice your safety performance. And here the green contour denotes another safe IO problem, which may have no tempting policies. For this type of problem, with empty tempting policy, we call them as non-tempting problem. So for this type of non-tempting safe IO problem, actually we can very easily to solve it by simply maximizing the reward, because if we just maximizing the reward without considering the constraints, we can easily obtain the optimal policy in that sense. And that's why we focus on the tempting problems in our in most safe IO settings. And apart from lemma 1, we also have lemma 2. The optimal policy of a tempting problem is always on the safety boundary. So here, our policy space is an extended policy space, and we consider the safety performance in an expectation form, which means for a particular trajectory sampled from the policy, it may not on the boundary, but if we consider expectation of the policy safety performance, it will always equal the constraint threshold you predefine. So here are two video demos to show the two lemmas. Here, the left one just show the optimal policy is on the safety boundary, and the right video shows a tempting policy. How does the tempting policy looks like? So the robot can achieve more reward, but it has to sacrifice the safety performance. Okay, then let's talk about the robust safe IO problem. So we consider the robustness regarding the observational space. We consider the problem that the observation of the agent could be corrupted by some unknown adversary. So the right video, the right figure shows the general diagram. The agent will make decisions based on some corrupted observation of the environment state. So it will execute the action that is corrupt based on some corrupted observations to the environment and receive the next state observation. We denote this new as an unknown adversary, which is basically kind of like function from state space to another state. And you can regard it as this setting actually mimic some realistic scenarios, like if we have a robot equipped with sensors, the sensors could be have some unknown noise that you cannot model them accurately, but they may naturally exist in the real world. And we have to emphasize that the true state of the environment will not be modified. So basically, the dynamics of the environment will not be modified. We only modify how the agent perceives the environment. And also, we need to make some assumptions for the adversary for the future analysis, because if the adversary is arbitrarily strong, it can modify any state to an arbitrary observation. Though this problem is very trivial, we cannot solve that problem. So a common assumption we make for the corruption for the adversary is that the corrupted observation should be within a perturbation set, the BS. And for example, if we use a LP ball perturbation set, it means all the corrupted perturbations should be within some should be close to the original observation within some LP norm. Okay, then let's see what are good attacks in the safe RL setting. So for good attack, we first define what is an effective attack. An effective attack means we want the attack to make the agent unsafe, because in safe RL we more care about the safety of the agent rather than the performance. And so this effectiveness is defined by the cost increase. If we introduce the attack to the environment, and apart from this effectiveness concept is very intuitive, we also introduce another kind of metric called stealthiness. So what does the stealthiness mean? We want the agent to be unaware of the attack. So for example, in many in practical applications, it's very easy to monitor the task performance of the agent. Say, for example, how much progress a vehicle can achieve during a limited amount of time. So this kind of metric is very easy to monitor. But for some safety signals, it may not that easier to monitor. So if the agent's reward drop significantly within a short time, then we may warn the agent that there exists some something's wrong. So we basically can alert that the agent the existence of the attack. So we basically want the agent to maintain its task performance while still can make the agent unsafe. So in that sense, we can make our attack more stealthy and make the agent unaware of the attack. So with the two concepts, let's first see whether the previous adversarial attack methods in the standard RL setting work. So this attack method called MAD attacker, maximum action discrepancy. This is a very popular and kind of sort of method for standard RL setting. The idea is to solve an optimization problem that can find the optimal. Oh, sorry, my cat is beside me. Oh. Sorry. Oh, he deleted a lot of my slides. Sorry about that. All right. So for this MAD attack, the basic idea is to find the optimal perturbation set within this the set that can maximize the KL divergence between the corrupted policy and the original policy. So the idea is very simple. So, for example, at a certain time step, we want to let the robot to behave differently from the past action. And this algorithm basically shows some implementation details of how to solve this how to solve this perturbation. And so let's see whether this adversarial attack method will work. We can see from this video demo. So indeed, so this testing policy is the same as the previous shown one, but we can see that the agent behave very abnormally by adding a very small perturbations. So we can see, although this attacker can make the agent like perhaps reduce its reward significantly, but we may not let the robot to violate constraints. So we cannot regard this type of attacker as effective and stealthy in the safe IO setting. So then we, based on the previous lemmas, we think about how to improve this MAD attacker. So recall that the lemma 2 said the optimal policy will be on the safety boundary. So we think if we only perform the attack in the high risk regions, meaning that we have some threshold like Kasei, and if the estimated values of the current state is above some threshold, which means it will be some high risk regions, we perform the MAD attacker. Otherwise, we will just let the agent to perform normally. By performing this AMAD attacker, adaptive MAD attacker, it can achieve better performance than MAD. So it means the agent can achieve good performance, good task reward, but violate constraint. And then we think how to design a more effective attacker. So here we introduce the maximum cost. It's very intuitive, and it's basically simply maximize some the cost Q value functions to obtain the optimal perturbations. And by solving this optimization problem, we can find that the agent may behave some dangerous behaviors. And we also introduce this maximum reward attack, which we want to emphasize. So because this attacker is kind of counterintuitive, because maximum reward is kind of like the optimization objective for safe IO. And in the standard IO setting, we usually want the attack to minimize the reward instead of maximize the reward. However, based on our lemma 1 definition, in the safe IO, all the tempting policies are unsafe. And the tempting policies are the policies that have higher rewards than our optimal policy. So we think if we can make the agent to gain more rewards, then we can also guarantee that it's unsafe. And in practice, it also works very well. If we apply this maximum reward attacker, the agent also behave, although it can achieve more rewards, but it's not safe anymore. And here is the comparison of different attacker methods in 4 environments. So the random baseline is to add some random noise to the attacker. And MAD, MCMR are introduced as previously. So for this figure, the x-axis is the perturbation range. It means that what kind of percent of what is the size of the perturbation ball in the LP norm. And the above the lower diagrams are the constraint violations, and the upper diagrams are the reward after attack. So we can see even in very small perturbation like 0.01, the MC and MR attacker can achieve very huge cost and also maintain the reward pretty well. And for some environments, it can also increase the reward, which means we can maintain the stealthiness of the attack. But for some other methods, like the random or MAD, for some even large perturbations, it cannot achieve. It cannot make the. It can hardly make the agent perform some unsafe behaviors. So this basically shows what are the strong attacks in a safe IO setting. So after we talk about the attack, then we think about how to against such attacker. So most simplest idea is to just perform adversarial training, and actually it works well. So for the adversarial training, we basically rule out the trajectories that is under the attack, and we use the corrupted trajectory to learn the safe RL policy. And after we learn the safe RL policy, we also need to update the adversary accordingly based on the most recent updated policy. So this kind of simplest mechanism works very well in practice for safe RL, for improving the safe RL robustness. But we have to notify that we have to note that not all the adversaries can robustify the policy to ensure the safety, and only the MC and MR attackers can be theoretically prove that it can, after the adversarial training, it can the trained policy is robust to any perturbations within the perturbation set. And we also show that some theoretical properties for why the adversarial training can work. It is because the Bellman contraction for the adversarial training for the Bellman operators under the adversarial training is still a contraction, so it can work. And if we apply the MC and MR attackers, we can ensure that the trained policy will not violate the constraint on any perturbations. So for the robust training method, there's actually a lot of previous methods proposed for standard RL setting. For example, for the SAPPO Lagrangian, for the SAPPO baseline, which is proposed in previous paper, their idea is to minimize the KL divergence between the corrupted policy and the natural policy. So it's similar to the MAD attacker, but you apply this MAD attacker in the policy learning, in the policy training part, and they show that their robust training methods can maintain the reward pretty well on the attacks. We will use them as a baseline method. And for the ACP Lagrangian MC MR means we replace their MAD attacker during training with our MC and MR attackers to show whether this training paradigm, whether this training method can work in the safe RL. And our method is called adversarial training PPO Lagrangian. So here shows the results for different tasks, and we schedule the two best algorithms with the gray. We schedule the best two algorithms with the gray color. So here we can see, we first see the natural column, which means the performance without attack. We can see almost all the methods can achieve pretty good safety performance. Like the cost is relatively low in the natural environment without any attack. However, if we apply some strong attack like MC and MR for the vanilla safe RL method, its cost is pretty high, and the PPO Lagrangian random is basically add some random noise during training. It still doesn't work very well. And for the baseline robust training methods, the ACPPO series, it still have very high cost compared to our adversarial training methods. So here are some like comparison between the for video demos to compare the performance of the PPO Lagrangian method before adversarial training and after adversarial training. So here is the performance in the natural environment as shown before, and the right one is the behavior after adversarial training. So we can see that the agent can somehow naturally, although it has a little bit conservative than the right one, than the left one. You can see the left one is far away from the, is very close to the safety boundary. But after adversarial training, the agent learns to keep a kind of safe distance to the safety boundary, which is an interesting phenomenon. So although we lose some kind of task reward performance, but we gain a much more robustness against and the safety on the attacks. So here is a comparison under MC attack, under the MC attacker. So the left one actually shows that the agent is not very robust against such kind of attack. But after adversarial training, our method can still finish the task very well without violating constraints too much. And this is a comparison under the MR attacker. It also shows the same similar behavior. So after adversarial training, we can also still maintain safety. It's actually performed very similar to the natural performance, which shows that the learner policy is actually pretty robust to this kind of noise. So the takeaways for this paper is that first, for safe RL, the safe RL may not be truly safe under adversarial perturbations in the observation space. So this actually poses some challenges for deploying the safe RL policy to the real world application, because the noise exists everywhere in the practical applications. And the second takeaway is that existing attacking and defense methods may not be very effective in the safety sense. And third is both the maximum cost and the maximum reward attackers are effective. Okay, we especially want to note that the maximum reward is pretty counterintuitive, and it's not very thoroughly discussed in the literature, but we regard it as a very strong attack in the safe RL setting. And the last one is that the adversarial training is very simple but helpful technique in improving the robustness in the safe RL setting. So before we move to the next topic, any questions?
Hi, 主席, there is a question from the chat window.
I saw a question in the chat. How will the simply increasing the threshold on the constraint work? Yeah, so that's a very good question. I also tried that one, but still, it's simply adding the making the constraint threshold stricter may not work in practice. So we can see this example. So suppose that our current cost threshold is like 20, and we want the policy to be more conservative and set the threshold to be 5 or 0. Then we can see for this on-run environment in the natural performance, the policy can learn a cost that is pretty low. However, on the attack, its cost may be significantly higher than the predefined cost. So simply decrease the cost threshold or making the policy conservative may not let the agent policy to be robust against the adversarial perturbations. So yeah, the reason is that the robustness and the safety actually are two different things you want to optimize. So although you can explicitly enforcing better safety performance by using a conservative threshold, but the robustness of the deep network policy may not be improved. So we can still find the weakness of the deep network to perform successful attack.
Thank you.
Yeah,
that's interesting because traditionally in engineering, people would just use a bigger margin of safety, and that's not sufficient here.
Yeah, the second question, the adversarial training seems to be a two-player game. It's very likely this runs into local minimum. Yeah, I think that's a very good question. So I think in the adversarial machine learning literature, we also discussed this. So why the adversarial training work and how to prevent, what is the optimization landscape for this adversarial training framework. So it's similar to other methods like GAN or other existing approaches. So it's pretty hard to analyze whether it's runs into a local minimum or what is the optimization landscape, especially involves in the deep networks. However, as far as we know that it is we can ensure its convergence by applying the Bellman operators for the so basically we have ensure that it can converge to a local minimum, And in that sense, it's still useful in practice. But how to better understand the optimization landscape of the adversarial training would be like a very hard topic for the whole field. Yeah. Another question. Have you tried to thought about combining MC and MR? Yeah, that's a very good question. So I actually already tried this one. So by linear combine MC and MR, and I also have a figure illustration in the paper's appendix to show that what is the safety performance. So as you said, we for some environments we can indeed achieve some trade-offs between the effectiveness and the stealthiness. And for some, and there also exist some sweet combinations between the MC and MR to achieve the most effective attacker. I didn't show the results in this slide, but if you're interested, you can check out the appendix for more results in this paper. Yeah. Okay. So then let's move on to the next topic. Let's briefly introduce another topic. So basically about offline safe RL. It's another relatively new topic that I want to briefly talk about. So first, why we study the offline safe RL? Because if we want the agent to freely interact with the environment to collect samples and learn the policy, it might be very dangerous. We can see how we cannot ensure that our agents may not perform some dangerous behaviors like this one. So we want if we already have those kind of dangerous data set, the data set contains some dangerous behaviors, we want to reuse that information in the policy learning. So we're interested in how to extract a safe policy from an offline data set. So the left figure is the workflow for the traditional safe RL pipeline. We will let the agent interact with the environment, collect a lot of samples, which probably contains a lot of unsafe data, and we do the training and we interact again. So we repeat this procedure many times to learn a good policy. However, the problem is that during the optimization, many previously collected unsafe data may be discarded after training, which is not very efficient. And the right one is the offline safe RL workflow. So suppose that we already have some previous interaction data set, and we store all of them and organize them in a database, and we use that data set to train a policy offline by many epochs, and then we can directly deploy this trained safe policy to some new scenarios to finish the tasks. So this is the right one actually shows an offline safe RL workflow. And so there are some benefits, as I mentioned, for this offline safe RL problem. So first is very economic. All the previous interaction data may not be wasted and it can be shared with others. And the second is that it's very scalable. We can use or modify some public available data sets to train our policy. For example, there exists a lot of self-driving data sets like Waymo's data set, Nuisance, or Argoverse. And if we can utilize those kind of data sets to training, and actually these companies have spent a lot of time and money and efforts, resources to collect those data sets. So it would be a waste if we do the safe RL in an online fashion. It's the most scalable ways to reuse this public available data set to train the policy for the self-driving task. And most importantly, we can ensure the agent's training safety by avoiding some dangerous interactions during policy learning. Okay, but there are also a lot of challenges for offline safe RL problem because it's quite different from the standard offline RL. Because in offline safe RL, we want to accurately estimate the safety performance of the training agent. So in fact, what we want to estimate during training is the cost value functions of the policy in this form. So here the trajectories are sampled from our learning policy. However, in the data set, the trajectories are sampled from a mixture of unknown policies that we may not know the true, like the probability or true like the policy weight of the behavior policy to collect the data set. So in that sense, without the online rollout, we probably cannot accurately estimate the cost values of the training policy. And in the safe IO setting, a subtle inaccurate estimation of the cost value could induce a very big difference for the resulting policy, because we can suppose that for the Lagrangian method here, if our value estimation is a little bit underestimated, the Lagrangian multiplier would go to 0, and which means it will not penalize the safety violations anymore. But if our value functions goes a little bit bigger than the threshold, then the lambda tends to be infinite. So it's actually pretty hard to accurately estimate the lambda, and to estimate this penalty weight for penalizing the constraint violations. And this is one challenge for offline safe IO. Another challenge is how to generalize the trained policy beyond one single threshold. So for previous constraint optimization-based methods, we usually need to fix the safety threshold before training. And after training, we will obtain the safe policy that satisfy this particular threshold. However, the data sets may contain trajectories with different threshold. And if we want to adjust the threshold for different scenarios, for example, in some scenarios, we want the agent to be more conservative, and for some scenarios, we want the agent to be like more we want to relax these constraint requirements. Then we have to retrain the policy from the whole data set again with a new threshold. So this is so consider that if we have a very large data sets, retraining the policy or refine-tuning the policy could be very computationally expensive. So we probably need a new training paradigm for the offline safe IO problem to address the two issues. So here we actually adopt the decision transformer architecture, which is very prevalent in the recent offline IO literature. So the basic idea for the decision transformer is it has two parts. The first part is it has a target return conditional policy learning policy training loss. So which means the input of the policy contains the target reward returns and the cost returns we want to achieve. And then by utilizing the sequential modeling capability of some deep network architecture like transformer, we can actually know that, okay, given your current targets, what is the most likely action I should take at the next time step? So based on these two capabilities, actually I found that the decision transformer training framework is very suitable to solve the safe IO problem. So more details I may not have time to introduce in this talk, but if you're interested, I list a lot of implementation details and why we use this decision transformer in the offline safe IO settings in the paper. So here basically shows what happens during the inference time in the decision transformer. So basically we have input sequence token, which is based on the target reward return and the cost return and the state. and we will get the predicted action based on the previous sequences of past tokens, and we will execute the action to the environment and receive the new reward and cost signals, and we will subtract the new received reward and cost to our targets, and we will append this one to our new token, new input tokens, and do the loop again and again until the episode is executed. So the benefits is that we can actually change the target cost return during the inference time. And what does that mean? It means we can basically achieve zero-shot adaptation to different cost threshold. So basically, after training, we can specify any cost threshold we want during the inference time. As well, I will show some experiment results in the experiment section. And also one important technique in this work is, so by the way, so naively extend the previous decision transform architecture by simply adding a cost token may not work well in the offline safe IO setting, because in safe IO we have to ensure that the safety. One problem is that we may encounter the conflict target reward and cost returns, because our the input should specify both the reward and the cost, the target reward and target cost. However, the conflict reward and returns may occur in practice. So which means that if we specify some reward return that is higher than our capability, so the agent may choose to either satisfy the constraint or violate the constraint to achieve the same level of reward. So actually, we propose some techniques to address this type of issue. For example, using this Pareto-based data augmentation methods, which can somehow address this conflict targets issues to make the training policy more safe. Okay, the time is not, I don't have too much time, so I will just briefly talk about the experiments results. So here the CDT is our method, and for the other methods, they are especially for the BCQ, Bear, CBQ, C dice, they are a classical constraint optimization based safe offline safe IO approach. So basically, we can see that for their method, their performance is either too conservative or too risky. So here we use the normalized scores. The maximum reward is 100, and the normalized cost threshold is 1. So basically means if the cost is below 1, it's regarded as safe. It is above, if the cost is larger than 1, it's regarded as unsafe. And the BC safe baseline is to only use the safe data set to train a behavior cloning policy. So actually, we can see our method can achieve like a very high reward while still maintain safety in all the tasks. And more importantly, the train the CDT policy can achieve zero-shot adaptation to different cost threshold. So here the x-axis is the target cost values. So for example, if we increase the cost from 0 to 3, here the dashed line means the maximum cost values we have in the data set. So basically, the left one is the interpolation performance, and the right one is the extrapolation performance. So the blue curve are our method, and the orange one is the baseline called the multitask behavior cloning. And we can see as the target cost increases, our real executed cost will also increase, and our reward will also increase, which greatly have a great balance between the safety performance and the target performance based on the user-defined targets. And also, after some target threshold, beyond some unseen threshold, the performance actually saturated to some point, so which actually is also a desired performance for this method. So, some takeaways for this work is that offline safe IO is actually a very it's a very new and also very important but challenging problem, and we have to reconsider the previous constraint optimization training paradigm because they have a lot of limitations for this new problem. And also in this paper, we think that the return condition, the sequential modeling methods are very suitable to solve this offline safe RL problem in learning adaptive and safe policy. And actually in this paper, we have more like insights and details, like how to characterize the difficulty of the problem and in what cases we should use in what data set and what problem we want to solve, we should use the offline safe RL. Actually, we discussed all the details in this paper. So if you are interested, you can check it out. And finally, yeah, so for the iClear paper, all our paper and code are public available. And for the offline safe RL paper, we will release the code very in the near future. So yeah, thanks for listening.
Thank you very much, Zuxin, for the great talk on the adversarial robust CMDP and the constraint decision transformer. So I'm wondering if there are any questions from our audience. Actually, I do have a question on the constraint decision transformer. I feel that this framework is I mean, the choice of the return and the cost target R1 and C1 are very critical to the performance. So how does this quantities like R1 and I mean the reward target and the cost target are chosen during the training and inference?
Yeah. So that's a good question. So as I said, so before training and after training, we first have to visualize our data set. How does our data set looks like? So we will plot the data set in kind of this map. So the x-axis is the cost return for the trajectories in that. So each point here represents a trajectory. So the x-axis is the cost return and the y-axis is the reward return. So after we obtain this figure, we can calculate the Pareto frontier, or we call this reward frontier values for different cost threshold. So in that sense, we can know under certain cost threshold, what is the maximum reward we could obtain, we could achieve for this task. And so even, but still, we may encounter some conflict targets during the inference time. So to solve this problem, we propose this kind of data augmentation methods by sampling some reward return pairs above this curve. And then we relabel this sample return pairs to the nearest Pareto optimal trajectories. So basically, if we specify a targeted return like this, the policy will learn to behave like this. So it's most rewarding, but also stay safe.
Yeah, thanks so much. And there is also a request from the audience that asking whether can you share the slides. Yeah, I think the Shangding will collect your slides and recordings and post it online.
Yeah, sure, no problem. Yeah. Okay.
So if there is no other questions, let's thank Zuxin again, and thanks so much for giving us great talks, and thanks so much for attending our online seminar. Yeah.
Thank you so much for listening.
Yeah. Thank you. Bye-bye.
Bye.